All right, welcome back. Today I'm going to cover the second section of Chapter 11, primarily dealing with the gas laws. I'm only going to cover 3 gas laws today, and then I'll cover a couple more tomorrow. But the 3 that I'm going to cover are Boyle's Law, Charles' Law, and Gay-Lussac's Law. And we're going to be taking a look at several different relationships here, but it's pretty simple. So the first one I want to look at is the relationship between volume and pressure in gases and how it's indirectly proportional to each other, provided that temperature remains constant. So you're just going to assume that in these problems with Boyle's law, that temperature is constant. So indirectly proportional means that as one goes up, the other one's going to go down. Or if one goes down, the other one's going to go up. And it's represented by the equation pressure 1, volume 1 equals pressure 2, volume 2. And it's basically multiplying these two together, and it should equal the products of these two. So if my volume decreases, I should see a rise in my pressure. If my volume increases, my pressure is going to decrease. So they're inversely or indirectly proportional to each other. So if I'm looking at a sample problem here, 2.5 liters of gas at 110 kilopascals is expanded to 4 liters at a constant temperature. What would the new pressure, or P2, be? So this is my V1, this is my P1, so V1 times P1 equals V2 times P2. So when I set this up, here's my volume 1 and my pressure 1, and it should equal my volume 2 and my pressure 2. So you can kind of see this is going to be very simple multiplication. So to solve for P2, you'd multiply these two together and then divide by 4, right? So you're going to divide by 4 here and here. So 2.5 times 110 divided by 4 gives you a pressure of 68.75 kilopascals. Now you can check this to make sure that you're right, because 2.5, I'm going to get my calculator here, 2.5 times 110, son of a biscuit, start over, it's 275. So if I take 4 times my answer, 68.75, I get 275. So I know I did this right. See, there's a way for you to check this on all of the gas laws. It's kind of cool. Moving on to second example. 650 milliliters of hydrogen gas is stored in a cylinder with a movable piston of 225 kilopascals, and the pressure is increased to 545 kilopascals. What's the new volume? So this is my V1, P1, and this is my P2, and I'm trying to find V2. So when I set this up, 650 times 225 equals V2 times the new pressure. So to solve, divide it by 545 on each side, and your answer is 268. So again, I can check this. 650 times 225, 146,250. All right. 545 times 268. Oh crap, that was not right. What did I do? Maybe I did my math wrong here. I probably did. So if I take 650 times 225 divided by 545. Oh, I know why, because I didn't round all the way. Okay, so if I take this times 545, yeah, that's pretty close. Whew, almost had a heart attack there. So that's Boyle's law. Moving on to Charles' law. Looking at the relationship between volume and temperature, they are directly related. That means if volume goes up, your temperature is going to go up, provided that pressure remains constant. So here's the equation for that. V1 over T1 equals V2 over T2. So as your temperature increases, volume increases, or temperature decreases, volume decreases. Now the thing I want to emphasize is that your temperature has to be in kelvins. So if you're dealing with a problem and they give you degrees Celsius, you have to convert. The conversion's really easy. You just add 273.15. So balloon with a volume of 15.5 liters, inflated in a room at 20 degrees Celsius, then taken outside where the temperature is 7 degrees Celsius. What's the new volume, provided pressure remains constant? So I'm going to set it up using the equation. Here's my V1, here's my T1, 20 degrees Celsius plus 273.15 to get to Kelvin. I'm trying to find my new volume. Here's my temperature, 7 degrees Celsius plus 273.15. So, figure this out. This is what my new temperature is like in Kelvin. Now to solve for V2, to get V2 by itself, I always like to cross multiply. I don't care what you do, but I always cross multiply. So 15.5 times 280.15 equals V2 times 293.15. So then something like this, right? So now I want to solve for V2, and to do that, you're going to divide both sides by 293.15. Okay? So I took the product of these two and then divided by the 293.15. Your answer should be 14.81 liters. Now, if I take a look at my volume before and after it went down, did my temperature go down? Yep, I went from 20 to 7. So my temperature decreased, so my volume should have decreased, and it did. And again, you could check your answer by taking 15.5 divided by 20 equals 14.81 divided by 7, and they should equal the same. Second sample problem for Charles' law. If the original temperature of a 62.2 liter sample is 150 degrees Celsius, what's the final temperature in degrees Celsius if the new volume of gas is 24.4 liters, provided pressure remains constant? So I'm going to set this up like this. Here was my original volume with my original temperature, but I had to convert it to kelvins. And then here's my liters with my temperature. So when I figure out what my kelvins was like, 150 plus 273 is 423.15. Now I'm going to solve for T2. Now to get T2, to kind of get rid of the fractions, I always cross multiply. So 62.2 times T2 equals 423.15 times 24.14, right? So now to solve for T2, you divide both sides by 62.2. So you multiply and divide, and your answer should roughly be 166 Kelvin. Okay, the final law I want to look at is Guy-Lussac's law, looking at pressure and temperature. Again, it's directly proportional, provided your volume stays constant. So instead of volume on top, we're going to have pressure on top. P1 over T1 equals P2 over T2. So as your pressure increases, temperature increases, and vice versa. Also, your temperature has to be in Kelvin. So the pressure in a tire is 101 kilopascals at 10 degrees Celsius. What's the pressure of the tire at 45 degrees Celsius, provided volume remains constant? So set this up. This was degrees Celsius. I'm going to convert it to Kelvin. So it looks like this. I'm converting both temperatures to Kelvin. That's all I did in this step. Now to solve, I'm going to cross multiply to get rid of the fractions. So 101 times 318 equals 283.15 times P2, right? Whoops, I always skip that step. So when I multiply across, this is a very large number. I'm sorry, Lucas. And then to get P2 by itself, I will divide by 283.15. And your answer should be 113.5 kilopascals. Two more sample problems. Pressure in a bottle of pop is 505 kilopascals at 20 degrees Celsius. What's the new pressure if we warm the bottle to 65 degrees Celsius? So when I set this up, I need to convert my degrees Celsius to Kelvin by adding 273.15. So that's all I did in this step, was figure out what my temperature was in Kelvin. Now I'm going to cross multiply. 338.15 times 505. It's a very large number, 170,765.75 equals P2 times 293.15. Get P2 by itself, you divide by 293 on both sides, and P2 equals 582.5 kilopascals. So really, I think all these problems is trying to, make sure that you have like the same conditions, like the before and the after lined up, and then just always make sure you have the right units. So, if you're dealing with kilopascals, well, your new pressure better be in kilopascals. Final sample problem. 600 degrees Celsius exerts a pressure of 1,515 kilopascals. At what temperature degrees Celsius will the gas exert 151.5 kilopascals? So I set this up, trying to figure out my new T2. To convert degrees Celsius to Kelvin, I got to add 273. So this is 873.15, and I should add a K here for Kelvin. All right, so I got it set up. I'm going to cross multiply to get rid of the fractions. So over here, I should have 1,515 kilopascals times T2 equals this very large product over here. Yeah, 132,282.225 kilopascals times Kelvin. To solve for T2, I will divide by 1,515 kilopascals on both sides. And my answer, T2, should be 87.315. All right, those are just the first of 3 gas laws. There's 5. So our next lecture, I'll talk about combined gas law as well as the ideal gas law. So you do have a short assignment. It's like 4 sample problems of Guy de Saxe, and then 5 sample problems of Boyles, and 5 of Charles. But again, it's very simple math. There's no conversions except for degrees Celsius to Kelvin, but that's just addition. So, but yeah, if you have any problems, make sure you reach out and get the help that you need.